The Big Bang, the story of everything. Time, the universe, us.
The Big Bang, one, has a cool name, and two, it's the history of our universe. This is it. It's all of us. It's all things.
That's the traditional view. But is it right? More and more scientists aren't sure.
In the old, outdated Big Bang theory, our universe just popped into existence from nothing.
We talk about it as the beginning of the universe, but what it really is the end of our understanding.
Astronomers are ripping up the old rules. But that creates new problems.
How can we possibly say that the universe expanded faster than the speed of light?
But are they asking questions with no answers?
What was the origin? Is there even a sense to asking, was there a time before time?
We don't know. We got none, folks. Well, we got some things, but it's tough. It's tough.
It doesn't tell us what happened really at the beginning. This is still an absolute puzzle.
So, just how did it all start? The Big Bang Theory is a good story, but is it true? To begin, at the beginning. No space, no time. Everything in the known universe compressed into a dot smaller than an atom. Suddenly, out of this, the universe expands. Stars and galaxies form, creating the cosmos we see today. The story of our universe starts with a Big Bang, or does it?
So the Big Bang is the observed truth, but there are details that haven't been quite worked out.
There are a lot of things that may have happened. It's just one explanation.
Science isn't about being right all the time. It's about being wrong. And we could absolutely be wrong about a major component in our understanding of the universe.
We're putting one of science's greatest stories to the test. The Big Bang sure sounds like an explosion. But was it? An explosion is a sudden release of energy from one point, usually generating light, heat, pressure, and a bang. But did the Big Bang even explode?
When you hear the term bang, you think of a noise, but you have to realize that it's sound waves propagating through air. So after the Big Bang, there's no air. There was no air, there's no way to hear anything. So in that sense, it was silent.
So the Big Bang didn't bang. But to make the universe, it must have pushed out stuff. Lots of stuff. Every explosion has an ignition point. What about the Big Bang?
So if you were to only think of the Big Bang as an explosion, you would very rightly ask, well, where's the center of that explosion? Where is the center of the universe?
There was no central point. There's nowhere in the sky you can point and say that's where the Big Bang was.
The Big Bang is everything. The Big Bang happened here, where I'm sitting. The Big Bang happened on the other side of the planet. The Big Bang happened in the Andromeda Galaxy. The Big Bang occurred throughout the universe simultaneously.
During an explosion, debris fires out from the center. This debris spreads out unevenly, with different-sized pieces landing at different distances from the blast center. But did the Big Bang shoot material out in this explosive manner? For clues, we need to search the night sky.
One of the things that's really very striking about the universe when you simply take a telescope and start looking in different directions is that it, roughly speaking, looks the same in all directions.
Although the universe is peppered with individual galaxies and galaxy clusters, the big picture is what astronomers call homogeneous.
When we say the universe is homogeneous, it means it's almost exactly the same on very large scales with very, very little differences. It's perfectly smooth.
If we believe the classic Big Bang story, the same amount of material was shot out over the same distance in all directions. Our smooth, homogeneous universe doesn't appear to be the result of what we know as an explosion.
It wasn't big, and it wasn't a bang.
The Big Bang was not an explosion like a grenade or a bomb or dynamite, where there is material rushing out from a common center.
It's not like there's a ring of galaxies that came out from some explosion.
A firecracker explosion is triggered by a fuse. So, what set off the Big Bang?
What I would say is there's no such thing as what triggered the Big Bang. You know, we tend to think when something happens, when there's an effect, there was a cause, right? There was something that made it happen. But here we're talking about the whole universe. There's nothing outside the universe to bring it into existence.
The science is clear. The universe did not start with an explosion. But if there was no bang, then how did everything start so small and get so big?
The young universe, we do understand. In the old contemporary universe, we also understand. We've stitched together this story where we don't fully understand the first few paragraphs of the story, but we know the rest of the book.
How can we get to the bottom of the Big Bang story when we can't even read the first page of the book? The only hope we have is to search back in time, line by line.
One of the amazing things about being a cosmologist is that telescopes are time machines. It takes a while for light to get here, so if we look farther out into space, we're really looking back into the history of the universe, and that's amazing.
The first clues to unraveling the Big Bang mystery came with the introduction of advanced telescopes in the 1920s.
Edwin Hubble was studying the light coming from distant galaxies. And what he realized was the more distant a galaxy was, the more reddened the light was. Why should that be? Well, it turns out that light reddens if a galaxy is moving away from us. It's called the red shift. So what he discovered was pretty much every galaxy in the sky was moving directly away from the Milky Way.
This was truly one of science's landmark moments. Hubble had proved one of the basic principles of the Big Bang story. Our universe is continuously expanding. There was only one conclusion to draw.
If you extrapolate that back in time, it looks like everything was coming from one point at one time. That's the Big Bang.
Hubble's discovery grabbed the headlines, but the idea of an expanding universe had been proposed 2 years earlier by a Belgian priest and physicist.
The real idea of the Big Bang comes from Georges Lemaitre. He realized that if you ran time backwards, back to the beginning of time, maybe everything coalesced into a single atom, the primeval atom.
Lemaitre believed the infant universe was extremely small and dense, squeezed into a single point. The primeval atom. Later, scientists would define this point as an infinite entity called a singularity. But there's a problem. The singularity and the laws of physics don't mix. It may be one infinitely small point, but it causes some impossibly big problems. The Big Bang. For almost a century, it's been science's leading account of how everything began. But there was no explosion, no bang, and it wasn't big. In fact, the father of the Big Bang, Georges Lemaitre, claimed everything originated from one tiny point he called the primeval atom.
I think one of the hardest things to grasp about the idea of the Big Bang is that everything you see, everything you've ever known, everybody, every house, every tree, every planet, every moon, every star, every galaxy in the entire universe, at some point 13.8 billion years ago, was compressed down into a tiny little dot.
In fact, far smaller than a tiny dot. Infinitely small. A point called a singularity. And this singularity has been causing astronomers headaches for decades. It's all because of one word: infinite.
As soon as you start getting the word infinity, things are infinitely large or infinitely small in physics, it means that you don't understand everything.
Einstein's general relativity predicts the theoretical existence of singularities. But in practice, a singularity is where our current laws of physics break down.
We do not understand singularities. These are some of the theoretical questions that are real conundrums, and people are trying to figure out what to do.
The universe is telling us something is going on here that we don't understand quite yet with our math.
Our mathematics are incomplete. This is a sign that general relativity is not up to the task of describing the earliest moments of the universe.
General relativity predicts singularities, but in reality, it doesn't work when things are really tiny.
Einstein's picture of general relativity is incredibly successful at describing the motion of planets around the sun, the bending of light around massive objects, the growth and expansion of the universe itself. But it breaks down when gravity gets too strong and gets too small.
General relativity may not be the best tool for understanding the origin of the universe. Say, for example, you want to weigh some spices in your kitchen. You use a kitchen scale. That works really fine. But now, say on the other hand, you wish to weigh your truck. That's just not the right tool for it.
So forget relativity. Maybe another fundamental branch of theoretical physics can help out: quantum mechanics. This deals with the small, the very small. But what about the infinitely small? Can quantum mechanics prove the existence of a singularity?
General relativity seems to say that singularities exist. They're a very straightforward prediction of general relativity. That doesn't fit well with what quantum mechanics says. Quantum mechanics tends to fuzz things out. It doesn't really like singularities.
In some theories of quantum mechanics, the science of the small, there's a limit to how small you can go.
For example, I'm not going to be able to fold up this paper more than 7 times. 1, 2, 3, 4. I'm feeling good. 5. Oh man. 6. Can I do it? Can I do it? Can I break the laws of physics? No, I can't. There's a limit. I just can't go past it.
You can't keep folding paper or space into smaller and smaller fragments. And according to most laws of quantum mechanics, you can't have anything infinitely small and infinitely dense. Singularities seem to be doomed. So is the Big Bang story wrong, or are we just too dumb to work it out?
Our laws of physics are our best attempts to model with mathematics all of our observations of the universe. The universe doesn't care what we think. The universe doesn't care how we understand it. This is just our attempts to explain the behavior that we see. And the earliest moments of the Big Bang is a big example of where our understanding falls short.
Maybe the answer lies in a combination of general relativity and quantum mechanics. But they won't play ball.
Imagine the rules of quantum mechanics are like the rules that lacrosse players might use to play their game. And the rules of general relativity are the rules that baseball players would use to play their game. If you're just watching a baseball game, then they're just following the rules of baseball or general relativity. If you're just watching a lacrosse game, you're watching the rules of lacrosse play out, you're watching the rules of quantum mechanics. But if you take one team from lacrosse and one team from baseball and put them together and ask them to start playing, they don't even know how to interact with each other. It's fundamentally different rules that simply don't connect. Each of these pillars of modern science, quantum mechanics and general relativity, are wonderful in their domain. But when we try to marry them, which is what we need to do to describe the earliest moments of the universe, it all goes haywire.
Perhaps both teams, playing with a unified set of rules, will shed some light on the Big Bang.
Merging together quantum mechanics and general relativity is the gold standard. It's what every theoretical physicist would really love to do in the modern age. We haven't done it yet. We have ideas. So when I say we haven't done it yet, we don't agree on what the right idea is.
What will ultimately reconcile quantum mechanics with gravity? Is there even a reconciliation between them? What do we need? Do we need more surprising, more powerful observations, new data that we weren't expecting, another genius or 1,000 geniuses to come along and find the route through the mathematics to marry it? It's probably all of the above.
So, a major premise of the Big Bang story remains unproven. But what about Monsignor Lemaitre's other assertions? Was the infant universe, the primeval atom, intensely hot? And if so, just how hot was it? The story of the Big Bang is based on the discovery that the universe is continuously expanding. And if we go back in time, this leads to one inescapable conclusion.
So if you run the clock backwards and let the universe get younger, it'll get smaller and smaller and smaller, and then everything is basically compressed into one point.
The Big Bang story claims this point was infinitely small. But scientists have not been able to prove the existence of such singularities.
In our universe, we see all galaxies receding from all other galaxies on average. Imagine if you were looking at trains leaving a station. If you ran the clock backwards, the trains would converge to the same station. Now, did these trains come from the same station? Probably. Did they come from the exact same platform? Probably not. You can't fit all the trains onto the same platform.
But while physicists can't prove everything came from an infinitely small and dense singularity, they're convinced the observable universe did expand from one small point, and this point was incredibly dense and incredibly hot.
Imagine that you and a bunch of friends are in a very large room, and you're all hanging out and it all seems normal. But now you're all crammed together in a very small elevator, and it starts to feel much warmer because you're interchanging all this heat. It's sort of like that in the early universe. Everything is smashed together, everything is very hot.
It makes sense theoretically that this period was intensely hot, but how do you prove it? How do you take the temperature of the early universe, which began 13.8 billion years ago? You can't, but you can take the temperature of the coldest part of the universe now.
So if you go away from all the stars and get away from all the galaxies, you might think space was infinitely cold, absolute zero. But it turns out it's not.
Empty space has a temperature of roughly 455 degrees Fahrenheit below zero, 5 degrees higher than absolute zero. Where did these mysterious extra 5 degrees come from? Big Bang believers thought they had the answer. They claimed this faint trace of heat was left over from the incredibly hot infant universe. Getting the proof took decades, but it came in 1964 by pure accident.
Penzias and Wilson were Bell Labs engineers, and they were given an assignment to measure certain radio signals for the idea of sending wireless signals via telephone, so rural areas could have telephone.
They used a radio antenna shaped like a giant horn.
The problem was, no matter where they pointed this horn, they kept hearing kind of a static, just a radio noise coming from every direction.
And they thought, okay, maybe it's a satellite, but it didn't match up with any satellite positions. There's a nearby army base, and they called up the army base, said, hey, are you broadcasting at this frequency? And they said, no, we're not. They thought maybe it's pigeon poop.
Well, there are these pigeons nesting inside the antenna, and their droppings are creating this noise in your telescope. So they actually went inside and scraped out all these pigeon droppings. But no matter what they did, the noise remained.
They tried everything they could to remove this background noise, and they finally realized it was coming from the sky. It was real.
What they were hearing was not radio waves, but a different form of radiation, microwaves, a heat signature left over from the Big Bang. They had discovered the cosmic microwave background, a ghostly snapshot of the early universe. Different colors highlight subtle variations in temperature. The cooler blue areas will develop to form stars and galaxies. The warmer orange areas will eventually make up the vastness of intergalactic space.
The cosmic microwave background is a literal baby picture of our universe. It's the equivalent of a picture of you when you were 7 seconds old.
We can date the cosmic microwave background to 380,000 years after the Big Bang. The temperature here is estimated to be 5,000 degrees Fahrenheit. But how hot was the Big Bang? As we run the clock backwards, the universe gets smaller and the temperature increases.
We know what the temperature of the cosmic microwave background was, but prior to that time, we know the universe was getting smaller and smaller and smaller, and therefore it had to get hotter and hotter and hotter.
But can we find out how hot?
In the early universe, it was much smaller, denser, and hotter than it is today. And in fact, it was so hot, it could fuse hydrogen into helium.
25% of the mass in the early universe is fused into helium in this timescale of just a few minutes. So it's trillions and trillions of times more than the amount of fusion that's going on in the sun.
Extremely high temperatures are required to fuse hydrogen into helium. Scientists estimate fusion started 100 seconds after the Big Bang, when temperatures reached 1 billion degrees Fahrenheit. During the very first fractions of the very first second of the Big Bang, some estimate the temperature could have reached 250 million trillion degrees Fahrenheit. But what sparked this massive release of energy here at the birth of the Big Bang?
The initial moments of our universe are a source of frustration, because it'd be really nice to know that, but also a source of curiosity. This is the frontiers of physics. This is where we're really pushing things to try to understand the fundamental aspects of reality.
But even if we can back up the Big Bang story by proving the way everything came from a tiny hot point, there's still another problem. Where did everything that made up that tiny point come from?
You can't get something from nothing, right? We all know that. Except it looks like we got everything from nothing. The entire universe seems to have appeared out of nowhere. How can that work?
The Big Bang. No space. Total darkness. Nothing. Suddenly, the universe sparks into life. Really? Surely everyone knows. You can't get something from nothing.
It's really the ultimate question. How did the universe come into being? And the thing is, we don't want just everything to come from nothing. It seems like a trick. But here we are, we exist, so something must have happened, and we just don't understand the physics of it yet.
This is one of the big open questions in cosmology, the origin of the universe. And I think that people have variously said stuff like, oh, the universe has come from nothing.
Like, ta-da, now there's a universe. But remember, we don't have data about the earliest moments of the universe. We don't know what was going on.
We're struggling in the dark. To get insight into what may have happened before the Big Bang, that period of apparent nothingness, physicists look to empty space. But does empty really mean there's absolutely nothing there?
It's not that there's something coming from nothing, because that old-fashioned idea of nothing just doesn't apply to what we think of as empty space.
It turns out empty space is far from empty. The vacuum of space is really a writhing sea awash with charged quantum particles and electromagnetic fields.
The vacuum of space itself, it can be a very dynamic thing. Matter can spontaneously appear out of the vacuum and then spontaneously annihilate.
The vacuum is full of particles and antiparticles that are whizzing into existence and then disappearing, colliding with each other.
Space is full of virtual particles, popping in and out of existence.
And there's no question that they're real. Their effects are absolutely visible. We can see them.
In extreme physics, things can get strange. Maybe nothing is something after all. If empty space contains particles that apparently come from nothing, could some sort of similar process have triggered the Big Bang?
The quantum vacuum itself can randomly, spontaneously, without any input, just have a lot of energy. Perhaps enough energy to spark something that we would call a Big Bang.
There are many speculative theories about the origin of the universe. But is its sudden appearance out of nothingness the only trick it pulled off? It also made matter from energy. The universe is full of galaxies, stars, planets, and comets. Where did they all come from? According to the Big Bang narrative, from one tiny dot.
When the universe began, there was actually no room for matter at all. The temperature was so high, the spaces were so compressed, that matter couldn't exist.
So how did the universe manage to become full of matter? In the primeval atom, there was no room for matter, but it was crammed full of energy. And as Einstein tells us, all we need to create matter is energy. According to E equals mc squared, energy and matter are interchangeable.
Einstein taught us, with special relativity, that energy and matter are two sides of the same coin. You can convert matter into energy by, say, blowing something up.
The most fearsome example of converting matter into energy was the atomic bomb, developed in the 1940s. But with the Big Bang, this process was reversed. Energy created matter. Matter that expanded out and out to fill a whole universe. And in cosmic terms, the universe, where matter would develop, grew remarkably fast.
Right after the universe was born, it had an unbelievable growth spurt, basically going from being a toddler to a teenager in the single tick of a clock.
How could the universe get so big so quickly? If we believe the Big Bang story, It appears to have broken one of the most fundamental laws of physics. Did the early universe really grow faster than the speed of light? In the classic Big Bang story, the observable universe expands from a ball of energy smaller than an atom. Today, the universe is estimated to be 93 billion light years in diameter.
Think about the vast universe that we see all around us today, and it was once a tiny, tiny little volume, unimaginably dense. The universe must have gone through a colossal growth spurt.
With a steady rate of expansion, there simply hasn't been enough time for the universe to grow to its current size. Regions of the universe that were close neighbors in the past are now so far apart that their separation can't be explained by normal expansion. And the huge size of the cosmos is not the only strange thing we've discovered. The universe is what astronomers call flat.
Our universe is lumpy and bumpy at small scales. There's galaxies, there's black holes, there's people, there's all sorts of junk. But at large scales, global scales, truly universal scales, our universe is flat.
Could this universal flatness and the super rapid growth somehow be connected? We know that the Big Bang wasn't an explosion, or matter in the universe would be unevenly distributed. Yet something pushed everything outwards and fast. But what? In 1980, Alan Guth, a young Stanford cosmologist, came up with a potential answer. His theory of inflation says the observable universe expanded from being smaller than an atom to the size of a basketball almost instantaneously.
In this tiny fraction of a second at the beginning of the universe, like a millionth of a second, but a millionth of that, a millionth of that, and a millionth of that, the universe expanded by, take the size of the universe at that time and multiply it by a 1 with, say, roughly 50 zeros behind it.
Inflation drove the accelerated expansion of the universe, made it get really, really big, really, really fast, and then it stopped.
Inflation seems to solve two Big Bang headaches: how the universe got so huge so quickly, and why it's so flat. Because it inflated everywhere at once, all the energy in the universe which would turn into matter was pushed out evenly at the same time and same pace.
And the first stars grow together to become the first galaxies. Even here, us in the solar system, we're born, we're seeded in the event of inflation.
Parts of the universe that are now separated by 93 billion light years once had the same cosmic zip code. To have expanded so quickly, inflation must have broken one of the fundamental rules of physics.
We all know that one rule the universe sticks to all the time is that nothing can travel faster than the speed of light. So how can we possibly say that the universe expanded faster than the speed of light?
But inflation says the universe expands into nothingness. There was no outside of the universe. The universe was everything. So space itself was inflating, and space can move as fast as it wants.
You can't go faster than the speed of light through space, but space itself is allowed to stretch and expand as fast as it wants. And that's what our universe is doing.
The idea of inflation smooths out the universe in kind of a peculiar way. You can kind of think of it as having a sheet with a lot of wrinkles in it. And if you take that sheet and snap it really hard, those wrinkles very suddenly flatten out.
The theory of inflation is one of the craziest sounding ideas in the history of science. So crazy that it might just be right.
Inflation helps us to understand the inexplicable, but there's a problem. We don't know what triggered or powered inflation.
The inflationary universe idea imagines that the universe was suffused with some kind of ultra-dense energy at early times, something that pushed the universe apart.
What caused there to be that hot, expanding stuff? We have to be humble and acknowledge that we don't know for sure.
But whatever started it, inflation was over in a split second.
It didn't last very long, and this is difficult to understand. How did inflation stop? We don't know. We got none, folks. Well, we got some things, but it's tough. It's tough.
But has the process of inflation really stopped? One radical theory proposes if the force called inflation kick-started the expansion of one universe, then why not another, and another, and another? Is inflation creating a whole series of new universes? Is there a multiverse? If we believe the Big Bang story, a dot smaller than an atom expanded to make a universe 93 billion light years across. A theory called cosmic inflation claims to explain this stupendous growth. But inflation may create more questions than answers.
Inflation gave us more than we had bargained for. We tried to come up with a mechanism that would just create our universe and stop. And then quickly realized that actually, just like most car factories don't produce one car and then stop, but produce many cars, inflation tends to produce one universe and another, and a vast number of them, a multiverse.
It's a process called eternal inflation. It proposes that while inflation ended in our universe and led to formation of stars and galaxies, we're just one small part of a vast, continuously inflating multiverse.
Imagine a series of bubbles next to each other. Those are the different universes. And so our bubble's expanding, and we're bumping into our neighboring universe, and we're going to expand into it, if the multiverse theory is correct.
A big bubbling multiverse sounds like science fiction. But there is prospective evidence to back up the theory. Scientists have spotted an unusual mark on the cosmic microwave background. That snapshot of the infant universe.
There's a spot in the southern hemisphere that's not necessarily the coldest spot or the biggest spot, but it's the coldest, biggest spot, and it's strange. We don't know how to fully explain it.
One unproven but intriguing theory is that this area is a kind of cosmic dent, surface damage from an impact with another universe.
I work in the building with the people that discovered this giant cold area, and they were pointing it out and saying, well, that doesn't make any sense. Why would the microwave background be like that? Hey, maybe that's evidence of another universe interacting with our own. That's something that when you go to lunch makes you pause.
If you buy into the idea of a crowded multiverse, cosmic bangs and scrapes are not only perfectly possible, they're probable.
There may be many universes outside expanding under the force of inflation right now. One analogy is think about a superhero that just can't be killed. They keep regenerating.
If the multiverse narrative is correct, It places a giant question mark over the story of the Big Bang. The possibility of a multiverse suggests not just one, but a whole series of Big Bangs. But not all physicists buy into this thesis.
The community is divided on the idea of the multiverse, predictably, because there are some of us who believe that this leap of imagination is justified. And there are others, sort of hardliners, who think that till we have empirical evidence, this is not a scientific idea.
Others welcome the fact that when it comes to explaining everything, we're not simply stuck with the good old Big Bang narrative.
I would have felt kind of claustrophobic if it turned out that all that existed was Earth. And I was happy that we discovered there was part of something bigger, the solar system, the galaxy, a cluster of galaxies, our universe. So I'd feel even better if there's still more space out there and in parallel universes. The more the merrier.
While it's an appealing notion, without empirical evidence, it's a theory requiring a leap of faith.
There's no reason to think that the tiny little creatures that we are actually perceive the vast true nature of reality.
This is still an absolute puzzle. We have ideas, I have ideas, other people have proposed models, right? But we have no data, really, that helps us distinguish between these ideas. And to be honest, the ideas themselves aren't fully fleshed out.
Support for the classic Big Bang model seems to be increasingly shaky. The latest thinking proposes not one, but a whole series of Big Bangs. As scientists continue to rewrite the traditional story, more and more questions are being asked. But for now, many remain unanswered.
What was the origin? Is there even a sense to asking, was there a time before time? And I think the answer is yes. You know, our science and our math, they're just incomplete.
Someday we may have the mathematics to describe the earliest moments of the universe. Someday we may be able to make predictions that we can connect to observations. Just because that day isn't today, doesn't mean that that day will never come.
We've learned an enormous amount in the last 100 years, but now we're left with some pretty serious puzzles that are going to be really tough to solve. So I'm waiting for the next Einstein.